Okay, let's get started. So I hope you guys, successfully submit the program assignment 1. TA will grade the programming assignment, so it may take some time for him to grade everything. But if you have any questions once you receive the result, anything you would like to doubt, feel free to let me know or reach out to the TA. All right? Okay. Yes. Yeah, I believe in the web course you only have like one spot. I didn't separate like the report and code. So what you can do is, if you. The report in the GitHub repository, so it's like just there. Oh, okay. PDF, it's labeled. Yeah, it's fine. So like if that's the convenient, right? You have the GitHub repository, everything, then you can put everything there. Yeah. Yeah.
You can do 2 files. I did it. Like you just drag and drop into that. There's like a tab called upload. Yeah. And then you can just drag and drop 2 files. Cool. I had done like it's like submit a link. And so like when you do the link, I was like, okay, put the link for the GitHub repository, put the link in there, and then it didn't have any other options for like putting a file in addition to that. Okay. And so that's why I just did the middle ground of putting the PDF of the report just in the GitHub repository.
I think you can upload document, right? So I think I did that setting correctly. So, but I can't double check. But either way, so as long as you have everything in there, yeah, it's fine.
Is a zip submission with everything in it?
Yeah, zip file is also fine, right? So like you can zip submit and put that in a Google Drive or like a OneDrive. That's totally fine. Yeah. Okay. Yeah, we can be flexible as long as you have all these documents there. Yeah. Okay. Okay, all right. So in the next couple of lectures, we'll talk about efficient deep learning from different aspects. Okay. So this is how we kind of see, right, how AI is able to transform biomedicine and healthcare, right? Especially, this case was able to using the AI to diagnose COVID cases, right? We can using these AI models, right, to do this kind of COVID-19, detection, and to kind of facilitate faster screening. Right, in this case, we are able to using GPT models, right, to upload some of the images and make some kind of good or well-educated, diagnosis based on the image, right? So these are all the success stories, like we've seen how AI is able to help in the biomedicine and healthcare domain. But we also witness, right, so the stronger model we get, but we all have this kind of consistent trend. That is, the size are getting bigger and bigger, right? So you have more parameters with your model, right? So like we have billions of parameters that is able to learn during the training process, right? So that increase the number of parameters, resulting a lot of computation, right? So we are measured by these this petaflops, right? So flops is basically the number of floating point operations, right? We are doing this kind of matrix multiplications, and we have multiplications and also additions, right? So these are the core operations when we train these kind of deep neural network model. And similarly for the memory consumption, right? Because you have all these large models and you do the backpropagation, right? So you have stored these kind of gradient, right? So all these memories also kind of scale very quickly, right? Due to the increase of the model size. And so then this will, face a lot of challenges, right? So essentially we need advanced infrastructure, right, to train these huge models, right? We are talking about billions of parameters, right? We have, extensive computational power and a memory resource to support this kind of large-scale training. So that's why, you can see nowadays is just a lot of big tech companies. They are competing with each other. They are releasing, they are keep scaling up the models, right? Competing each other and to But in a lot of labs or maybe in the university settings, we don't have a lot of resources, right? So this kind of large-scale model training is not going to be feasible if we don't have a lot of resource. And speaking of in the healthcare setting, right? So a lot of hospitals, especially in this kind of under-resourced, hospitals, right, or the developing countries or areas, right? They are lack of necessary GPU resources, right? Sometimes they don't have a GPU, workstation or computer at all, right? They only have like CPU machines, right? So which is significantly less efficient, right, for deep learning tasks, because we all know these some deep learning architecture or some of the toolboxes, like essentially the CUDA, right, is optimized for the GPU, processing. But in reality, that this kind of resource disparity will prevent some of the models being trained or even deployed on some of the settings. So if we do want to leverage some of the AI, or using some of the AI capabilities, right, in the healthcare setting, right? So for example, the hospital want to using some of the AI to help maybe streamline their process or to improve their efficiency, right? If they want to using this kind of model, then they probably have to do some sort of infrastructure update, right? What if I don't have these powerful GPUs? Then I have to purchase maybe some GPU servers or workstations, right? So that's involve a lot of cost. And this kind of infrastructure overhaul is not that easy to be achieved, right? So because you need have the money to purchase, or you also have some of the policies or regulations to be approved. So it's better we think about from the algorithm side, right? How can we reduce the computation rather you change the hardware architecture? So given these constraints, right? So we see efficiency are really important, right? When we deploy this model in the real life scenario, right? So for the example, we are talking about medical image analysis. So just to give you, or maybe we can dive a little bit deeper, right? So now we know there's sort of like a big picture, right? So if we keep scaling up these models, then we are facing this kind of computation and memory bottleneck. And what are the more concrete issues we have to maybe separately conquer, right? So one is with all these large models, right? And in the real life, right, we have very diverse resource or platforms or devices, right? So we have these drones and we have the cell phones, right? Smart cameras, right? So these are the varying resource devices, right? So how can we deploy a model on these diverse resource device? And second is we have a lot of pre-trained model, right? So like maybe some of the deep neural networks are pre-trained on ImageNet, and we want to leverage that in our application, right? So in our case, we want to leverage these pre-trained model maybe for medical image analysis, right? So as we mentioned, right, some of the state-of-the-art or later will be learn from like these foundation models. They are pretty huge, right? So fine-tune these models for the downstream task is going to also be very computation and memory consuming, right? So because we have to basically tune all these weights in this large-scale model. And also, if you want to train your own foundation model, right? Let's say I want to train a foundation model for specific medical applications, then I want to leverage all these different data modalities like text, maybe radiology report, different type of images, right? CT, MRI, all these imaging modalities to train a foundation model for medical diagnosis. Then with all these multimodal data, then you have a lot of training cost. This will also have some detrimental effect in the environment, because training these large models on days or even months, there's a lot of CO2 emissions, right? So actually there's a lot of report. Now AI actually emit all this kind of green gas more than like the cars, right? We are driving on a daily basis, because a lot of data center train these large models. They have a lot of CO2 emission. So this is also from the environment or sustainability point of view, we have to think about, right? So how we are able to reduce these kind of training costs in a sustainable way. Okay, so all these issues we'll talk about in the next couple of lectures. But first, let's look at this one, right? So we have this is very common, right? So we have a lot of different devices with different computing capabilities. Then how can we deploy these models, right, to fit that specific computing budget? So to address this issue, right? So then there's already a lot of research focused on the efficient neural network design, right? So okay, I don't have a lot of computation or memory resource, then I want to design some efficient neural networks so that is able to cope with this kind of resource requirement. And to achieve this, there's a couple of ways we can, kind of design, right? So how we can make these neural network more efficient. So one is we can do this network pruning, right? So by the name, we know that a lot of deep neural networks that is over parameterized, right? So you have a lot of parameters, but not all of them may be necessary, right? Some of the neurons may be redundant, right? So you don't need that many of the neurons in your network. So basically we can remove, right? So we can prune some of the unimportant neurons so that we can make this network more slim, so that it will consume less computation and memory. Another way or another path is we can specifically design some efficient network architectures. So for example, here we have some dedicated neural architecture like a MobileNet, ShuffleNet. They design some specific operations. So they kind of tap into the basic building blocks, right? Like for the CNN, we have the conventional convolution, right? So how we can make the conventional convolution more computation efficient, right? So they make those changes to fundamentally make the network, efficient. And we can also do, quantization, right? So reduce the precision. Usually, we are talking about this kind of full precision training, right? So we are using this kind of 32-bit floating point, precision to train the neural network. But sometimes maybe you don't have a lot of computation or memory, right? So we can reduce the precision, maybe quantize into like 8-bit. And to the extreme case, you have this kind of binary network. So the binary means you only have like two values in your weight activation, right? Either can be 0 or 1, right? So you don't have these kind of other choices, right? Okay, question?
When is there a need to do full precision, like 32-bit precision? What use cases?
So, I mean, if you have a lot of, computation or memory resource, you always want to using the full precision, right? Because this kind of gradient backpropagation, the accumulation, if you cannot support a longer bit stream, right, longer length, then you have some round-up error, right? In this case, this error can be compound, right? So like, for example, you have a very extreme case like binary or even 4-bit. So you can imagine, right? So how many choices you have, right? So this depends on your application, right? So if your accuracy is really important, I cannot sacrifice my accuracy, then probably you have to using the full precision, or at least most of the layers, right? You want to using the full precision to make sure a lot of them are, have the accuracy ensured. But if you don't have a lot of computation, right? If you are flying a drone or using the cell phone to do a lot of heavy computing, then you have to maybe balance the computation and also the precision together. So that's some of the use cases. Yeah. Okay, so that's another kind of a tuning knob or factors you can consider to make your neural network efficient. And lastly here, there's another approach called a knowledge distillation, right? So basically, you have like a teacher network. So usually this will be like a very large, heavy network, and maybe doing this kind of full precision training. And you also have a smaller, maybe a low or quantized version, right? So in this case, you want to kind of using this teacher network to distill the knowledge from the teacher to the student So during the deployment stage, you don't have to deploy a large teacher network. You can deploy these learned student network, supposedly may be able to achieve comparable performance as a teacher, right? So in this case, you don't have to deploy a very large model, right? So you can deploy a much smaller student model. So that's the knowledge distillation. So for this class, we'll talk about some of the key techniques under each of these design strategies. Okay. So first, let's look at a couple of efficient network architectures, right? So they are specifically designed by taking into the efficiency into account. So the first one is the mobile net, right? So by the name, this network is designed for mobile application, right? So you want to run a convolutional neural network on the cell phone, right? So you can maybe perform very intelligent tasks, right? So for example, you're taking a photo, you want to detect different objects and maybe figure out which one is the foreground or background, right? So which one you want to focus on, right? So so you want to run this kind of neural network with very minimum latency, right? So you don't want to wait a couple of seconds, then you can take a photo, right? So you basically want to still, let the user to take the photo instantaneously, right? So this is their objective. So for this mobile net, they specifically come up with this kind of depth-wise separable convolution. Okay, so maybe we can just quickly recap, right? So what is the conventional convolutional kernel or filter is doing, right? So here we have a spatial resolution or the filter kernel size as dk by dk, right? So typically we have like 3 by 3 or 5 by 5. And you also have the channel dimension, right? So because different layers, they have different input feature map number of channels. So you also want to match that dimension, right? So you usually have like IM different channels, and then you apply n such filters, right, to generate n different output feature map. So that's the conventional or standard convolution filters. So in the mobile net, so they basically come up with like a two-step operation to reduce the computation. So one is called the depth-wise convolution filter. Okay, so in this case you have m this kind of dk by dk by 1. Okay, so now each of the kernel only have a channel dimension of 1. Okay, so you only have one channel dimension, and you have m of them, and we'll talk about that in the next slide, how this can be operated. But just here, just to give a preview, right? So they have this kind of operating on the depth dimension with dk by dk only, but they have m such filter. After that, they will do this kind of 1 by 1 or the point-wise convolution, trying to mix up or aggregate the channel dimension information. So let's dive deeper into how these depth separable convolution works. Okay, so here just to using a figure to demonstrate, right? So the conventional convolution, you have this one, right? dk by dk by m. You basically sliding these convolution across the entire feature map, right? So eventually you will generate, if you have n filters, will generate output by dg by dg. So this is the output dimension, right? So you may have some, if you don't have a padding, you have a strided convolution, you may reduce reduced like feature map, right? You have n of these, so you're resulting in feature map. So let's look at how many multiplications we will result, right? So for these conventional convolution, because later we'll see how these separable convolution is able to reduce the number of these computation, right? So let's work together, right? So for this one, right? So I have a couple of questions listed here. So this is the standard convolution operation. So how many multiplications are there in one position? Can you compute that? So for this particular position, right, how many multiplications are there? So if the kernel size is dk by dk, and we have m channels, right? So for one position, how many multiplications are there?
dk times dk minus 1 times m.
So that's dk squared times m, right?
Does it depend on the stride?
So just one position, right? We are not, so we are not trying to compute the entire. So one position, right? So just this very first position, we have, because for each of the channel, right? So we're doing this kind of, atom-wise multiplication, right? So we have dk squared times m, right? Then the next one is, what if we slide, this kernel across the entire feature map? And I also tell you, the output feature map has the size of dg times n. So that's the output feature map size.
So dk by dz is kind of like a stride number?
No, the dk by dk is the kernel size.
Oh.
And the output size is dg by dg times n.
The number of multiplications into dg squared?
So I tell you, like, this is output feature map size, right? So this is my kernel size. Then how many total multiplications, for this one particular kernel over the entire input?
dg into dk squared into n?
Yes. Because the output size determines, right, how many position. dg by dg determines, right, how many position you actually kind of sliding across, right? So that will involve, different stride, will result in different output feature map size. So you have output feature map size spatially, right? You already know that's dg times dg, right? So basically you sliding across dg square positions, right? And the last one is simple, right? So you have n such filters, you multiply with n, right? So that's, the total number of multiplications you have if you apply n such dk by dk times m convolution kernel for this particular feature map, okay? So the depth-wise separable convolution here is, the idea is we want to reduce the number of computation, right? So this is really time-consuming, and that consume a lot of floating point operations, in the whole network training. So we want to reduce that, right? So in this depth separable convolution, the first step is depth-wise convolution, right? So we know that now they using dk by dk by 1 and using m of these different kernels. So what they do is you are no longer operating across the m channels, right? So you're basically treating these m channels separately, one by one, okay? Like the first channel, I apply the first dk by dk, right? First channel will only have channel dimension 1, so I can apply this dk by dk sliding through the entire feature map, right? Then I get a new feature map, right? Then for the second feature map, input feature map, right, I'm still consider a single channel dimension. So I will use the second kernel, right, dk by dk. So this dk, the original, these kernel weights can be very different, right? You don't have to be necessarily the same. So this can be a different dk by dk kernels, and times has the channel dimension of 1, right? Because we are only looking at one channel at a time. So you can imagine, right? So we have m of such dk by dk by 1. So you are also able to resulting m different feature map. So just to visually give a more concrete example, right? So here we have like input 12 by 12 by 3, right? You only have 3 channels. So you apply these depth-wise convolution, you have 5 by 3, 5 by 5 by 1 filter. And you apply this individually to a channel. So here I'm using this different color to code that. The first is orange, only apply to the first feature map. The second is red, right? So only apply to the second feature map. You apply your resulting second feature map, which is red color, and the third one, right? So apply to the last feature map, and your resulting a new feature map, which is color coded as yellow. Yeah, so you basically just apply this to the first channel, then you result in this one, right? So every dimension matches, right? So channel dimension is 1. I only have one separate feature map, right? And I can, scan through the entire spatial domain. I just generate like a reduced, right, 8 by 8. So apply a second kernel map, right? This can be a totally different set of weights, 5 by 5, right? Apply to the second one, then I generate the second feature map, right? So in this case, I still generate like the same number of channels of the feature map. Okay, so this is basically, if we go to like, M, right? So we apply M of them. So that's why we apply M such filters in the depth-wise, right? So by the names, we are only applying this depth-wise, which means like we are treating each of the channels separately.
The depth of the channel and the number of the filter must be matched.
Yeah, because you apply individual, kernel, for each of the feature map, right? So the depth here is M, right? So here we have to apply M such filter. Okay. Okay, so one thing you might notice, right? So in this case, let's still using this very concrete example is that, before the conventional convolution is we have, depth-wise, right? So we kind of aggregate all these different channel information together, right? So that's why we can learn all these informations within this input feature map. But now we are separating, you're treating each feature channel individually, right? There's no information flow through different channels, right? There's no communication between different feature map channels.
Spatial positional things here. Is this that was the problem conclusion are losing any information pushed to the channels?
No, so here we don't have any of the channel information. So my point here is that the conventional convolution, they aggregate multiple channels, right? But here we're only treating individual channels by itself, right? So we're not looking into other channels, right? Maybe other channels will provide also very useful information. So that's why the second step is called point-wise convolution. Okay, so remember, by doing the steps-wise convolution, we are resulting this dg by dg by m output feature map. But the problem is that, these feature map, they never, talk to each other in the channel-wise, right? I only talk to these elements within each channel, right? We are not talking, it's like you are never talking to, your classmate maybe next door, okay? You only talk within this class. You talk to each other, but you never talk to student next classroom, right? So you want to encourage that as well. So in this case, you have these, point-wise convolution, right? So basically, in the spatial domain, it's a 1 by 1. Right, so now you can see why design this way, because we want to encourage the channel-wise, the depth-wise communication, because spatially we already do this kind of aggregation. So basically here you have a 1 by 1 by m, convolution, and you apply this across this entire feature map, right? So basically you are aggregate all this information across these M channels, right? Because it's a 1 by 1 convolution. And you can apply n such filters, right? So you are resulting n feature map, okay? So you apply n 1 by 1 point-wise convolution, and you resulting n feature map, right? So because if you apply one of these, you resulting a single feature map, and you apply n of these, you resulting a feature map like this. Okay. So now we can also do the similar thing, right? We can compute how many multiplications, and also we can also consider like additions as well. But here, let's just for simplicity, we can compute how many multiplications are there. We are not going to do this step by step, but I just give you like a total. We have this many multiplications, and with that we can do the comparison, right? So we can maybe compute the ratio, right? If we do comparison with the standard convolution, and this is the ratio we are getting. Okay. So if you plug in some specific or maybe commonly used sizes, right? Like 3x3 kernel are commonly used, right? So we have the dk equals to 3, and n could be the number of filters that are typically used, right? Like 1024, and you can see that, right? So this is kind of effectively reduce the number of multiplication by a factor of 10, right? So you only have like 1/10 of the multiplication as compared to the original or the standard convolution. So that's a significant reduction of the computation. So that can really improve the efficiency. Okay, so that's the idea of the mobile net, right? So they are using this depth separable convolution and the point-wide convolution to first do this information aggregation within each channel spatially only. Then we are using the point-wise convolution trying to aggregate information from different channels, okay, using these two separate steps to reduce the computation. And here are some of the results they are getting, right? So of course we want to measure the number of these floating point operations, right? How many multiplication and additions in terms of millions. And we can see that MobileNet reduced as compared to the conventional convolution like GoogleNet or VGG, reduced that significantly, right? And also the performance doesn't suffer, right? So the MobileNet has ImageNet accuracy 70.6%, right, as compared to GoogleNet, even higher, a little bit higher, right? And for the VGG, you can see that VGG may be like 30 times number of computation as compared to MobileNet, but only gain less than 1% of accuracy. So I think this is really a good trade-off, right, in terms of efficiency and accuracy. So the next, network called a ShuffleNet kind of have very similar idea, right? So the key idea is that right now I'm dividing the original feature map, right? So the k by k by n into subgroups. Okay, so I can divide them into like a G group. Okay, and basically I will apply a convolutional kernel within this group. Okay, so you can imagine the stepwise separable convolution is, this G is equal to n, right? So, right. So within each group you have the one channel, but in this case they kind of increase the the number of channels you're looking at within group. Maybe you look at like 5 channels as a group at a time. So you apply a convolution, within this group, right? So you have a channel dimension of 5. So you can do this kind of a group-wise convolution. And so this figure illustrating, right? So you have basically like these many channels in total, right? So you divide them into like 3 groups, and then you apply these kind of convolutions within individual groups, right? So you generate these kind of output feature map. But the similar problem will appear, right? So although you kind of increase the communication a little bit as compared to this depth-wise convolution, but these channel-wise communication only occur within this group, right? So the red group only talk, the channels only talk with each other within this red group, right? They never talk to other like green or blue channels. So in this case, to encourage, right, the information or mixture, So they basically using this kind of channel shuffling, procedure. So basically, you can kind of randomly rearrange these channel dimensions, right, before you go to the next group convolution, right? So here you just basically randomly shuffle them, and you get this kind of mixed, you kind of reordered channel dimension. Then when you go to the same like group convolution, in this group you already have like a mixture of from other groups, right? So here we have a different mixture of colors. So in this case, hopefully by doing this a couple of times, then different channels get a chance to be in each of any of these particular group. Okay, so that's the shuffle net idea. Okay. So the next is called the ghost net, right? So their key motivation or inspiration coming from the observation of some of the feature map. So they observe, if let's say I apply maybe 512, kernels, and I generate feature map maybe look like this, and they notice some of these features are very similar to each other, right? So like the red color box highlighted. So they are very close to each other, right? So these green box highlighted, so like the structure, the shape, they look the same, right? This blue one, they look the same. So it seems like there's a couple of redundancy here, right? So some of the kernels or filters learn very similar feature patterns, right? So they generate some of the redundancy, and we don't need like a separate kernel to learn that, right? So basically, if I know I have one feature made like this, then maybe to getting this kind of feature, I can maybe do some very cheap operation, maybe just do some scaling or adding a specific value, right? Doing some very cheap operations. Rather, you're using a network, another different filters to learn, right? So that's their key motivation. So in this case, you can,
Can you go a bit deeper?
yes.
So the feature map generated by this residual group, this is the first group. Like when I give the images, this is the output of feature map of the first block.
No, this is a different network. So we are talking about, this is the feature map. You mean the first layer or something? Mm-hmm. Not necessarily the first layer. So that can be like a later layer or something. So, but I forgot which layer they are visualizing this.
I just want to know, like the first row of the image and the last row of the image, are they coming from the first layer?
No. So this feature map coming from the same layer. So let's say this is ResNet 50, maybe the last conv layer feature. So their observation is that there is some similarity in these feature map, right? So these kind of highlighting, they are similar, right? So then in their idea is that, okay, so because of this kind of redundancy, right? So maybe we don't necessarily need like 512 feature map, right? Let's just using half of them possibly, right? Because there's a lot of redundancy there. So we can reduce maybe the feature map by half. And but I do want to maybe enrich the representation, right? Instead of using another half of learnable filters to generate features, in this case, I can using some very cheap operations. So they are using so-called this ghost module, right? They are using very cheap operations. So this 51, 52, or 5K are not kind of learnable, like using a conventional convolutional kernel to learn the feature map. Rather, for example, you can do this kind of linear combination of these two, right? So I can simply do some linear combination of these two existing feature map and generate another one. So this may look like something, I may combine these two, right? Maybe resulting a feature map like this, right? So this could be a much cheaper, operation. Rather, you're using a kernel, right, to slide it across the entire feature map to generate this one. But you can just do a simple, weighted average between these two, or maybe other cheap operations to generate a new feature map. Okay, so essentially, this is what their main idea, right? So using some of the cheap operations to kind of enrich the feature map. And this is some of the result they have, right? So they are counting. So in the horizontal axis, right? So this is the floating point operations, and also the vertical is the accuracy, right? So as you can see that across different floating point operations, right? So they are able to achieve the best trade-off, right? So you have under each of the floating point, right? So they are able to achieve the best accuracy. Okay. So and talking about transformers, and we also can think about similar design, right? So how we can maybe make your transformer more sparse, right? You don't have to using too many tokens to do this kind of self-attention. And so, I think when we talk about, transformers, we mentioned a couple of, like you can using the flash attention, right? So they have right now have a V3, flash attention V3 that is also integrated in the PyTorch. They are considering some of the hardware specifics to make it more efficient, right? And they are also designing some specific architecture that is able to accelerate maybe some of the models, right? The segmentation, anything model, they're using the efficient VI2 to help these models to reduce the computation, okay? So that's, some of the very classic or widely used efficient network. I think a mobile net is still widely used in the industry, right? So, basically that's like the default or go-to model. If you want to deploy something on edge devices, right, the mobile net is kind of tried and true, very effective. So people are still constantly using the mobile net. And the second strategy is we can do pruning, right? As we mentioned, we don't necessarily need these kind of very large, network with all these different neurons. So we can kind of remove some of the maybe redundant or non-important neurons, right? So basically, we can measure, right? So how the magnitude of these kind of activation, right? How large is your weight, right? If the weights may be close to 0, which means doesn't activate too much, doesn't contribute too much to the learning, then we can basically remove them, right? So we can remove these close to 0 weights, and then you resulting like a sparse network. Then you can repeat the process. Okay. Of course, so then close to 0 is just like a design principle. So basically, you can choose a specific like threshold, right? How large you want to make sure you keep that weight. Yeah. Question.
I had a question about the separable convolutions.
Yes.
Is there a way to, like, for example, we have a trained network. It already has a kernel for a particular convolution operation, right? So can we convert like already trained weights to like the separable convolution forms?
Well,
Not train separable convolution from scratch and just reuse the trained weights to somehow refactor it into.
I mean, there's some reparameterization tricks, right? So like you can reparameterize some of the kernels into something during the inference, but I don't think, if you want to do this in the depth separable fashion, because these are like two separate operations involving like two steps. So that probably have to, require some retraining. So I don't know if you kind of force that into this kind of depth separable, because the internal mechanism, how they work, is totally different, right? If the network is already trained in a conventional convolution, but you repurpose that or converting that into the depth separable, there's some disconnection there. So
heuristic would be a better approach.
What's the word?
So to do this, we cannot like directly do this because there are two different operators.
Yeah. So yeah.
To do it, we can maybe use something of a heuristic to get a decent enough starting point for retraining.
Yeah, you can do something like you can have a validation set to measure, right, the performance, just to monitoring, how you want to train to some point or retrain to some. If you maybe you don't want to do a very extensive retraining, and maybe by converting this, you are not totally destroying some of the learned representation, but you just need to do some later adaptation, right? So maybe you don't require a full run of the retraining. So you can use some of the mechanism to monitoring that, yeah, to do some light retraining possibly, yeah. Okay, so this is the process for the pruning, right? So basically you want to filter out those weights that doesn't contributing too much, right? By measuring the magnitude of the weights. If it's very small, then you can basically remove that by setting a certain threshold. Then you can repeat the progress, to a certain desired, sparsity. Let's say I want to trim the network into like 50%, right? So you can repeating the process until these, first 50% of the neurons has been pruned out throughout the process. Okay, so this way is called like unstructured pruning, right? So you basically pruning individual neurons, right? So you may be resulting a very unregular network, right? So this layer maybe have all the neurons, and this layer maybe have like 30%, and this layer maybe 10%, and they are not very structured, right? So the issue with this kind of unstructured pruning is these kind of result may not necessarily the best for the hardware, right? So a lot of hardwares, if these neurons acting, in different positions, is not able to fully take advantage of some of the speeding mechanism or some of the modern library, right? So, or hardware. So they are specifically designed for this kind of structured network. But this is a very unstructured, then the speed may necessarily, gain some of the speed you wish. So there's a theoretical gain by pruning this, but actually during the hardware implement, you are not get the full potential. Okay, so sometimes you want to consider like structured pruning, right? Instead of removing individual neuron, maybe you want to remove the entire layer, right? Okay, so still your network can be structured, right? But you just remove the entire layer, right? Because this may not be necessary. Okay. And here we have some of the result on these kind of network pruning, right? So for this VGG network, right? So this is the baseline network, and this is 17% pruned, right? And we are measuring test error, okay? As you can see that we are able to reduce the number of parameters and also significantly reduce the computation, right, count. And we are not sacrifice a lot. Actually, this test error even going down, right? So you have originally like 6.3% of error, but now we only have like 6.2 error, a little bit improvement, right? So this pro network actually have better accuracy and also enjoy a much better efficiency, okay? So these are different neural networks, right? Like you have a dense net, ResNet, and put pruning at different ratios, right? So like 40% of prune, 60%, right? Maybe you have more extreme case, you want to prune like 90%, right? So of course, this will definitely, if we prune a lot, right, that will definitely, affect the performance. So I think to your question before, right, like if you want to leverage some of the mobile net, instead of like, reparameterization, you can also consider, pruning the mobile net, right? So maybe you can further reduce the number of parameters for the mobile net without sacrificing the accuracy a lot, okay? So yeah, here another paper, right, shows you like state of the art of neural network pruning. So if you're interested in network pruning, you can check this paper. Next, we want to also talk about the network quantization. Okay, so that's basically we want to reduce the precision. Okay, so for the quantization, we can roughly divide these methods into two categories. So one is the quantization aware training, and the second is the post-training quantization. Okay. So the quantization aware training is basically you do the quantization during the training, right? So you have a pre-trained model. I want to, this pre-trained model may be full precision, okay? I want to make it more efficient so I can run on the edge device. So what I do is I will reduce maybe the full precision into like 8-bit precision, right? So I do the 8-bit quantization. What I do is I will using the same training data, right? Because I do the quantization, a lot of these kind of gradient of weights will be changed. So, but I using the retraining to kind of gain the performance to make sure, once I do the quantization and with the training data, I can still achieve a very comparable, accuracy. Okay, so that's quantization aware training, right? So you do the quantization during the training process to gain to maintain the accuracy. Another method is, if you cannot afford retraining the network, right? So you don't have that for example, maybe you don't have access to the training data, right? That is used to pre-train this model, right? So then how we cannot do this kind of, quantization aware training, right? So you can also only do this kind of post-training quantization. So basically, you have this pre-trained model, then you quantize into a specific position, but you do have some, we call this kind of calibration data, or you can think of this as kind of validation data, a small set of validation data to help you do some light training, right? To kind of gain some of the performance, right? So you using this calibration data to calibrate your model weights, and so that once this is quantized, you are still able to achieve a very good, accuracy or performance. So as you can see, these two different strategies you can imagine, right? So this quantization aware will mostly give you better performance, right? Because you have access to the original training data, and you are train, these neural network, during the quantization process, right? You do the quantization during the training, so you basically optimize the efficiency and the accuracy at the same time, right? But the post-training quantization is that you just do some light fine-tuning, basically, using a different set of validation data set to do some calibration. So usually the post-training quantization will result in a worse accuracy, or mean your accuracy may drop, more. Okay, so that depends on your use case. And this figure shows you, right? So if we do this kind of quantization, right, so we can achieve, better energy efficient, right? So basically, this is how many energy consumptions, measured, right, for different operation, right? This 5-bit addition, 32-bit addition or multiplications, right? So a lower bit resolution definitely will consume much less energy, right? So this is really important, right? So for some of the edge devices, right? So especially for some of the devices like a microcontroller, right? You can imagine microcontroller only have megabyte, memory and have very low resource computation. And, if they are operating on the battery basis, right, then you want the energy consumption to very minimal so that you don't have to switch, battery very often. So one particular example is the Ring camera, right? So I don't know if you guys, install the Ring camera at your home, right? So the Ring camera, they have some object detection, person detection, functions, right? So, and usually the Ring camera, they are operated using the battery, right? You have to charge, although it's a rechargeable battery, but you don't want to recharge the battery every 2 or 3 days, right? If you heavily use that algorithm. So they have some optimization there in terms of these neural network design and also quantization to minimize the energy consumption, okay? So that's one particular example. Finally, I want to, talk about, knowledge distillation. Just to kind of also touch upon this kind of pruning, quantization. This pruning, we talk about the CNN, right, to using the activation. I think this also applies to if you are using the transformer architecture, like the vision transformer. So basically, we can reduce the number of tokens, right? So because the number of token effect, because we have the self-attention, that is quadratic computational cost, right? If you can reduce the number of tokens, then you can reduce the computation a lot. So what you can do is you can reduce the number of tokens, right? Because some of the tokens may be related to background or homogeneous region, doesn't contribute a lot to the representation. So we want to remove that. So basically, you can learn some of the like a policy network, like a small MLP layer, to score each of the tokens, right? Is this token is going to be an important token, or this is going to be easy token, right? So then this policy network, a very small MLP, can be joint optimized in the entire network in the end-to-end fashion, right? So you can view that MLP as a separate layer to optimize which token I want to reduce for a particular transformer block, and so that I don't suffer the accuracy, but I also enjoy the efficiency. Another is you can consider like a token merging, right? So some of the tokens may be serving the same purpose. You can measure the feature similarity, right? The cosine similarity between the tokens, and maybe trying to merge them, right? Basically do some weighted average between them, so you can reduce the tokens as well. Okay, so those are some of also the strategies you can apply in the transformer architecture domain. Okay, so let's talk about the last strategy, right? So basically that's the knowledge distillation, right? So basically means I want to distill or transfer a knowledge from maybe a single large model, or maybe a set of large models, to easy to deploy. Usually it's a very lightweight model without significant loss in performance. Okay, so this is a diagram show you the idea, right? So teacher network, right? So by the names, right? So teacher may possess a very rich knowledge base. Right? Usually this is achieved by using a very large over-parameterized network. And a student network is the one we eventually want to deploy on the real application, right? So this is very small, lightweight. And so this knowledge distillation is we want to trying to distill or injecting the knowledge from the teacher to the student, so eventually they can achieve very similar performance, right? If they can achieve similar performance, then in the inference stage, I can deploy the smaller student network, right? So I can get rid of this teacher just using the smaller network. So there's a couple of ways to distill the knowledge, right? So that's the case, right? That's the objective, right? So how can we make the knowledge from teacher transfer to the student, right? So how can student mimic the teacher to achieve similar performance? So the simple way is we can do this kind of logit distillation, right? So here, logits can, for a classification problem, this can be like the output classification probability, right? So you have that vector indicating the probability of this teacher network. And we are assuming these logits are very accurate, right? Because teacher has a strong representation power. They usually make a very confident, accurate prediction. And student, we trying to make sure the logit mimic the teacher network, right? So here we can using some of the metric like called the KL divergence, basically measure the discrepancies between two distributions, right? So this is the KL divergence measure these two distributions, how different they are, right? So here we can basically trying to minimize these KL divergence, right? So if the student predict the logits or the prediction very similar to the teacher, then that's a good thing, right? So that's kind of student mimic the teacher behavior. And so, basically by minimizing these KL loss, eventually we want the student network trying to behave like a teacher, okay? So in addition to this kind of last layer, like the logit distillation, right? We can also try to facilitate this kind of knowledge transfer in the intermediate layer, right? So like the feature map. So the teacher maybe have like 152 feature representation, feature maps, but the student only have like maybe 5 or 10 feature map, right? How can we injecting the knowledge from these many feature maps into like a small number of feature maps? Right, so basically, we can maybe do some pooling and get a high-level feature representation, and we can also do the pooling for the student, get a feature FS. Right, we trying to make sure they are as close as possible. Right, so if I can using two feature maps to achieve a very good representation similar to the teacher, then this should make sure that the output prediction should also follow similar, right? Because all these feature representations, I closely follow the teacher, right? So that can also make sure the predictions also follow the teacher network. So this is kind of like an intermediate knowledge distillation, right? Rather just only the last largest distillation. So that's the idea of doing the knowledge distillation, so that you can train in this way. Then during the deployment, you can deploy a student network to make them efficient. So here are some of the results, right? So they are doing a teacher network, right? So basically, this is a larger network, right? So you have like ResNet 26, and a student network is ResNet 8, right? So you only have like 8 layers. If you train this student network, right? So the baseline, you train this from scratch using the data set, you have like 87.9 accuracy. But if you're using the knowledge distillation, right? So you can see that after the knowledge distillation, you get like 0.87% improvement, right? By distill the teacher network, right? So you have ResNet 26. You are able to boost that performance, to like almost 1%, right? So in this case, you enjoy a lightweight network, but you also enjoy the knowledge from the teacher to have a better performance. So of course, they try different like teachers, right? Like a strong teacher or weak teacher or something like that. So this is something, there's a lot of research, right? So like what kind of teachers you want to select, or maybe you don't want just a single teacher, right? So you can have like an ensemble of teachers, right? Just like a different expert to teach a student how learn some, unique knowledge from different teachers or robust knowledge from different teachers, so that the student can have a very good performance. So some very active research there, how you can do this kind of teacher-student distillation. So just come to the medical domain, right? So as we motivated earlier, right? So medical domain or healthcare domain, this is really important because a lot of infrastructures are very old, right? So hospital settings, we don't have this kind of advanced computing resources, but we do want to using some of the advanced AI models. So in this case, we only can do is from the algorithm side, right? To distill or to make the model more efficient, so we can deploy in some of the old architecture or hardware. So for this particular application, they are doing the image segmentation, right? The medical image segmentation. They are using this teacher-student knowledge distillation framework, right? So you have a heavy teacher network, and you have a smaller student network, right? So they are not just doing the logit-based, right, like the ground truth mask-based distillation, but they also have some kind of intermediate knowledge distillation. So this, they design some specific distillation module, right, like importance map distillation and region affinity distillation module, right? So basically taking into account that specific characteristics of medical images. Right, for the segmentation, we care about different regions, right, that are contour. Right, when you talk about medical image segmentation, the metric, right, so we have these, dice scores, right, we also have this Hausdorff distance, right, so measure the boundary. So that's similar. So they are also want to take into account not just maybe the dice score, but some of the boundary region information, how we can also using that to enforce the student is able to learn or behave like a teacher when we talk about small details. Okay, so that's some of the unique design they are doing to facilitate this knowledge distillation. And this is some of their result, right? So they have dice scores, and these also using the number of parameters as a measure, right? So if you're able to reduce the parameters, right? So you can also reduce the computation. And here are some of the results they show, right? So, with the student network, right? Without any of the knowledge distillation, then you may miss some of the segmentation, or you may have some of the wrong segmentation, right? But with this knowledge distillation, with the teacher, is able to behave very, or make a prediction more accurately, right, as compared to the ground truth, okay? So that's a used study, for using the knowledge distillation for medical imaging. Of course, there's many other papers, right? So maybe using other strategies, maybe doing the quantization or network pruning, or maybe, combine a couple of strategies together, right? Remember, all these techniques not like dependent on one another, so they can be used in combination or orthogonal to each other, right? You can do knowledge distillation, or you can also do pruning, quantization, right? You can do this simultaneously, or maybe you can do this in a different step, right? Do the quantization, or maybe do specific efficient network design, then do the quantization or network pruning to gradually achieve the goal, right? So you have a certain, efficiency requirement, okay? Okay, so that's all for today. So hopefully this will be, interesting, right? So because, for a lot of, real life activities or applications, we do require this efficiency, right? We cannot say, you have a very powerful network, but we cannot use in some of the application, okay? Any questions?
Seems like on quantization, pruning, and this, it's more a comment, but seeing all these technique, what they do is like knowledge distillation is like they start from a large model that have everything already trained and have all the knowledge, and then they start going down.
Mm-hmm.
It's not like they start from a small network and
Mm-hmm.
train on that or quantize.
Yeah, so if you think about if you have a small network, so it's like the learning capacity is already being determined, right? So you have this data set, you train on that data set. The learning capacity is there. You cannot go beyond that. But if I have a teacher, a very significant large network, is able to injecting that knowledge has been already extracted, distill that to you, then this student can maybe get better performance. So I think that's, the idea of, either doing the distillation or, doing some of the quantization. So, but, another way is, you can think about efficient network design, right? So that's a totally different paradigm, right? Like a mobile net. So it's just basically how you can come up with more efficient operations, right? But not necessarily sacrifice the learning capability, right? So that's another direction to pursue, yeah. But I think now a lot of times, people maybe go to this kind of knowledge distillation. It's kind of quick, right? So because you have a lot of large or foundation models at your disposal, right? You can using them to distill your small model, and this can be done in once, right? Because you are not like training or distill like many times. Doing once, then you can deploy a decent model for your application, right? So I think that's. But one thing I think a lot of research right now is they also thinking about hardware and software co-design, right? So like it's just like a vision transformer, like a transformer accelerator, right? So I want to accelerate the transformer, not just from the algorithm side, but I also have to look into the hardware design. How specifically they do like 3x3 or this kind of attention matrix multiplication, right? How the memory cache is working. Then how I can design a specific algorithm that is able to better fit this hardware structure, right? Like you are doing GPU or FPGA or maybe other hardware, etc. So there's different directions or route you can pursue. Yeah. Okay. Okay. All right. Thank you, everyone. So I'll talk to you guys on Thursday. Okay.